Today I want to apply game theory. So now we've spent 2 lectures already talking about game theory. And today I show you some really neat applications. One is car traffic. So it's not really social network, but it's very interesting. So I'll show you how drivers in the roads are players, and the strategies are the travel route. So each driver decides what route to take, and all the drivers together, you can see it as a game, okay? And the shorter the travel time, the better. So the payoff will be the negative of the travel time, so that it's the higher better. Okay? And I'll show you a paradox. Actually, this is actually really well known now, but it was a big paradox a few years ago. When you add roads to a traffic network, you could make the travel slower. So you think adding a lane or adding a road is always a good idea. It's not. It can make things slower. And the reason is because it adds new strategies. And the strategies can give problems. Like, remember the prisoner's dilemma? Each driver tries to make kind of an optimal route. So this makes Nash equilibrium. And so this is considered a paradox, but it's not really paradox because you can understand it in game theory. Okay, so that's the first one. The second thing is even more interesting. This is auctions. Les ventes aux enchères. This is really, really popular on the internet. So in an auction, you have a whole bunch of people who are bidders. They bid some money, and the highest one can get it, for example. And this is used a lot. And there's 2 kinds of auctions: first price and second price. So you will learn a lot about auctions today, and we're going to analyze it with game theory. So let me first talk about car traffic. Okay. So you have a transportation network. This is a directed graph where you're drawing on the roads. The nodes can be like decision points or places on the traffic network. And each edge is labeled by the time, how long it takes. Okay. Like in this one, going from A to D takes 45 minutes. Going from A to C depends on how many cars there are. So we're going to do a simple model. The time is x divided by 100, where x is the number of cars. The more cars, the longer it takes. Okay? So this is a linear function. Of course, in real life, it's going to be nonlinear. It increases, and eventually you get a congestion, and it goes like that, so that it even works. But we're going to make it just a simple model to already show you the paradox. So here's an example. Assume you have 4,000 cars driving from A to B. Okay? And if they take the upper route, if they all go through C, then this AC will be 4,000 over 100 will take 40 minutes, and CB will be 45 minutes, so it'll be 85 minutes. But if they split between the two, half and half, then this one will be 20 minutes plus 45, 65. This one will also be 45 plus 20. Then it will be only 65. So you see, it's better if they split, if they go half and half. Okay? So you can see how the driver's decision results in payoff. And all the drivers are deciding at the same time which path they will take. Now once they leave A, the decision is made. Okay? So this is a game. The drivers are players, and the strategy is the route that they take. And in this is a simple one. Each player has 2 possible routes. They go through C or they go through D. Okay? And payoff is negative of the time, so higher payoff is better on lower time. And the difference between last week is that there's a huge number of players here. We don't just have 2 players, we have 1,000. Here we have 4,000 players. But it's still the same kind of a game. Okay? We're going to talk about strategies, dominant strategies, mixed strategies. Nash equilibria is still applying to this in a nice way. Okay? Okay, now this game, let's look at the Nash equilibria. We can show that any set of strategies where the drivers are balanced, 2000, 2000, between the 2 routes, is a Nash equilibrium. And we can prove that. We're going to prove that. So any time you have 2000 going this way, 2000 going that way, it's a Nash equilibrium. So how many are there? How many Nash equilibria does that make? A lot, no? Did you see any kind of combinatoric analysis? How many ways can 4,000 cars split where 2,000 go up and 2,000 go down? Combinations. Remember combinations? So the number of combinations of 4,000 things, which are the cars taken, they have choices one at a time. So you have 4, you can write it like this, 4,000, choose 2,000. So the number of Nash equilibria is a lot. If you have a good calculator, you can calculate that. 4,000 factorial divided by 2,000 factorial squared. So that's a huge number. So there's a huge number of Nash equilibria here. Okay? And we can prove it's a Nash equilibrium when you have 2,000, 2,000. Remember, what is a Nash equilibrium? Each driver has no incentive to switch. That means when a driver switches, it gets worse. So it's an equilibrium. Each driver, if it is picking their best thing. Okay, we can prove that. Actually, that's not so hard to prove. So let's say we have strategies where X drivers, some number, use the upper route, and 4,000 minus X are going to use the bottom route. So X and 4,000 minus X. Okay? Now, if X is different from 2,000, then the times for those 2 will be different. Because here we have X over 100, and here we have 4,000 minus X over 100, so they're not the same. So if X is different from 2,000, the times between the 2 are different. That means any driver on the slower route will have incentive to switch to the faster, so it's not a Nash equilibrium. Okay? The driver going on the slower one, which is more than 2,000, if I have more than 2,000 go down, each driver has an incentive to switch because they do better on the other one. So that would not be Nash equilibrium. But if X is equal to 2,000, then they have no incentive to switch. So then we have a Nash equilibrium. You see how neat it is. The Nash equilibrium covers very nicely the driver's selfish decisions. So there's a huge number of Nash equilibria there. Okay, so that's nice, right? And all the drivers will take 65 minutes. So we can analyze this. This is like a game. Okay, now let's modify this and see what happens. Okay? So in the previous case, we had perfect balance. Let's now add a new road from C to D. Okay? We add this new road. The government says, we'll try to make things even faster. We'll build a very fast highway from C to D. okay? And it's so good that we'll just say the time is 0, okay? Just for showing the example. It's very efficient, okay? Now, when you add this very fast highway, you might think that travel time will go down, okay, for people. But no, it doesn't go down, it actually increases, gets worse. Everybody's travel time gets worse. And why is it? Well, it's because people are selfish. Each person tries to pick their own best route. Okay? In the new network, there is a unique single Nash equilibrium, but it has a worse time for everybody. Okay? And every driver will go through C and D. Okay? And that gives you a time of 40 plus 0 plus 40, which is 80 minutes. Okay? And the drivers, this is a Nash equilibrium, and we can show that by saying if the driver switches, the time gets worse. Okay? So if one of the drivers switches and goes here like this, they will have 45 plus 40, they will have 85, which is worse than 80. So all the selfish decisions of the drivers will put them all on the CD highway, and they will all take 80 minutes. But in the previous, without the highway, it was 65 minutes. So it got worse. Okay? It got worse with this new highway. Okay? And the reason is that it's not, Nash equilibria is not a global solution. So again, it's like prisoner's dilemma. Each player maximizes their payoff with their rational, selfish decision. And so that pulls them all into CD. And the overall strategy is worse. Okay? So this is called Braess's paradox, because there was a traffic researcher called Braess who saw that in 1968. He goes, whoa, what's happening? Okay? So you can kind of see the fast highway from C to D, it pulls everybody in. So it's like a vortex. It's a dominant strategy. Okay? Nothing is better. It's always better. But that is a local, selfish thing. Globally, it gets worse. So there's no way that self-interested behavior by the drivers will get back to this very nice, balanced solution. Okay? So adding resources to a transportation network can hurt the performance. And this has been observed. So this is not just a theoretical thing. This really happens. And you can see, and there's many examples that you can find on the internet. So here's one example. In Seoul, in Korea, they built a public park some years ago, and they removed a 6-lane highway to do that. So there was this big highway going into the city. They got rid of this highway, so boom, people were protesting. And so this was called the Cheonggyecheon Restoration Project. Not sure exactly how to pronounce it. But destroying that highway actually made the travel into the city better. It improved travel time. So it's a win situation. They have a nice park and the travel is better. So the 6-lane highway was like not very good idea, okay? So you can see, analyzing this thing is important. So this is a real practical benefit you get from this, okay? So this happens a lot. The possibility to worsen behavior by adding new routes occurs not just in traffic, but many areas, and you can all analyze it using game theory. So I'll give you a couple of examples. So in electric power grids, you know, there's you have generators, you have distribution, and there's a huge grid covering the country, covering all of Europe, okay? And it's decentralized, so you have separate generators and many distributions, and sometimes you have choices. Adding additional links can reduce the transmission capacity, the amount of gigawatts that they can transmit. By adding extra links, you can reduce it. And it's because sometimes if you add big links, they will be like vortex. They will absorb all of the capacity, and all the selfish decisions by the generators, by the distributors, will go through the extra links, and like for the traffic, and it makes things worse. Okay? Okay? So if a new line is built to connect two generators, this changes their relationship, and it has an effect overall the whole network. So the decisions of how to move will change. Okay? So this is important because now we're transitioning to wind power and solar power. So some countries have huge solar already. Like Denmark, for example, has already more than 50% of their average power is generated by wind. It's not bad, huh? In fact, wind is very stable once you get off of the ground, 50 meters or more. And if you make it offshore, like in the North Sea, no one sees it, it's no hindrance. But you need a lot of wind generators. So a large number of small generators. So the power distribution is changing, okay? And so you have to be very careful that you don't make things worse. So you have to analyze it using game theory when you make wind power. Okay? And then there's a few other really totally different examples. In biology, if you have a bunch of species of animals, plants living in an ecosystem, you have what's called a food web, where you can figure out which species is eating which, and it makes like a graph. If you say one of these species is doomed, it's going to go extinct. But if you remove it, sometimes it can actually make things better by preventing more extinctions. Okay? So again, it's a complicated situation. Okay? And also in sports, you can see this. So for example, basketball team. A basketball team is like also a network. If you want to score a basket, there are certain ways to do it. So you have possibilities. So you can graph these possibilities where the ball goes between different people using their talents, and then they score. Okay? And each person has a different efficiency. And so adding a very good player, a star player, could actually make the team do worse, could reduce the overall efficiency, even though the star player is very good. So it's like this example. Even though the CD route is very good, the whole gets worse. So that you can see in basketball. In soccer, you see it. And actually, this actually comes around. So there's a manager, Lenio Herrera. He sees that in his team. He says, with 10 players, our team plays better than with 11. That's very possible. That's not a fluke. That could really happen, okay? Okay, so let's explain a little bit more where this paradox, why it's not really a paradox, okay? The idea is you add a new strategy, adding a new strategy to an existing game will make things worse. And we kind of saw it already in the prisoner's dilemma. Remember, if they both confess or not confess, so if they both not confess, they will get a small penalty, but if they both confess, they'll get a big penalty, but because of the selfishness, they will both get the big penalty, okay? And there's actually been theory of studies on this, so I can give you a theoretical result. So assume the travel time is a linear function. So if you have a number of cars x, the time is ax plus b. Then you can prove that if you add edges, you can get a time that's 4/3 higher, at most 4/3. So there's a limit, okay? So this is a limit, but it's worse, okay? So this is what you get when it's linear, but in real life, it's more complicated. It's nonlinear. Once you get, if x goes up to a certain level, the time goes really much higher. So it's more like a nonlinear function, and then it can get much, much worse. Because if you go on to this part of the nonlinear function, it can be much higher than 4/3. So you can really make it much worse. So for example, if this CD highway is congested with 4,000, the zero time will go up, okay? So this, it can get even much worse. Okay, let me give now just a more concrete example with prisoner's dilemma. So remember prisoner's dilemma? So this is the way game we saw. You have two suspects. Confess, not confess, not confess, confess. So we saw this before. And if each one does selfishly, they would both confess. Because if I do not confess, the best response to that is confess. If I do confess, the best response to that is confess. So confess, confess is a natural equilibrium, but you get -4. Whereas if you don't confess, you get -1. So assume that you have a simple game on the top, where you only have non-confess. This is like a simple traffic network. Only have non-confess. Then it's always -1, -1. Now if you add an extra possibility, so you've added this new possibility, it makes the result worse. So giving the people more choices can make things worse, okay? And it's because the selfish choices are not global optimum, okay? So this is, it's actually very simple to see using game theory, okay? So this is interesting, the Braess paradox, okay? So that's one example. Now let me go to auctions. Auctions, which are another really big area where game theory is important. So let me tell you some stories on auctions first. So auctions are very old, and archaeologists have found a lot of evidence, at least 500 BC. In ancient Babylon, women were auctioned for marriage. That's pretty nasty, right? In ancient Rome, you would sell off spoils, pay a debt with auctions. Vente aux enchères was very popular. In modern times too, auctions are very important, very popular. Ships, artworks. There's a famous tulip bulb auctions in the Netherlands, where a single tulip bulb can be enormously expensive. There was like speculation on the tulip bulb, and it's kind of like the cryptocurrency, the NFTs of today, because this tulip bulb is not worth so much, but somehow there was a bubble created because of the auctions of tulip bulbs or other goods. And today too, Christie's and Sotheby's, famous auction houses, they sell art, okay? And other things, governments will auction off things, frequency spectra. So the government makes a law on certain spectrum of radio frequency, but it's not the government who's going to exploit, it's the companies. So the government sells licenses, but how much do the licenses cost? Nobody knows, so they make an auction, okay? And another one, today, online auctions, e-auctions. This is very common, much more than you might think. Okay? They break the physical limitations because it's all virtual, okay? You can be all over the earth, don't have to be physically present. There can also be huge audience. It turns out, this was in 2002, but probably today the number is much higher, even higher than that. Online auctions were 30% of all e-commerce was auctions. That's a lot, okay? In search. When you search for something through Google, auctions will happen, but it's behind the scenes, these auctions, okay? You also have sites where you explicitly do auctions, like eBay, but the real big number of auctions is happening behind the scenes, okay? Okay, so let's show you something about auctions. So we're going to learn about auctions. So what is an auction? An auction is one seller selling one item to a set of buyers. And the buyers will bid for that item. And one of the buyers is then selected as the winner and will get that item. Okay? So one seller and a set of buyers. You also have the opposite situation. One buyer and a set of sellers. This is called procurement. So the government wants to build roads, or they want to build, or NASA wants to build rockets, but they won't actually do the fabrication. They make a procurement auction. So they ask companies to bid on building the rockets. So here it's the NASA that's paying, and maybe Boeing or Lockheed or McDonnell Douglas or SpaceX or whatever will bid, and then the government or NASA will pay. So that's the opposite situation, but it's still an auction, okay? So we're going to talk about the usual kind of auction where you have one seller and a set of buyers, okay? So we're going to make some hypothesis, a model for this. We assume that each bidder has a value for the item. So, for example, somebody is selling an artwork, a famous sculpture by Antonio Canova, whatever, very famous sculpture, and each bidder has some value for that in their head. This is called the true value, okay? So that the bidder might think this is worth 5 million euros in their head. So the bidder is willing to pay up to 5 million, but no more, because otherwise they would be losing money in their head, okay? So the true value is like the maximum they bid, okay? So you have the true value. Okay, so that's one concept. The true value of an item. So each bidder has a true value. Okay, now there are actually, what kind of auctions exist? There are 4 main kinds of auctions that are done, different kinds of auctions. They're called ascending bid auctions, English auctions, descending bid or Dutch auctions, first price sealed bid auctions, and second price sealed bid auctions, which are also called victory auctions. So it's kind of many ways of doing auctions. So maybe you have experience in some of them. So the ascending bid auction is the one that you can see, for example, in James Bond movies. There's a famous James Bond movie called Octopussy, where they are selling Fabergé eggs, which are like jewels, very rich jewels, and there's an auction going on, okay? So this is an ascending bid auction. This is interactive. So you have the seller selling that egg, and the price goes up, and the bidders keep bidding, and when the price is too high, the bidders fall away, and when there's only one bidder left, they win, and they pay the price of that bid. Okay, so that's ascending bid. But there's also another kind of auction, which is called descending bid, Dutch auction. So here the seller lowers the price, starts from some really, really high price. Okay, nobody's bidding that, nobody's buying. They slowly lower the price until some bidder says, okay, I want it now. And the first one that accepts is the one that gets it. Okay? Both of those are interactive. So they're like over time, it's happening interactively in real time. There's also two options where it's not interactive. This is called sealed bid. All the bidders write down a number, stick it in an envelope, and they give the envelopes to the seller or to the organizer. They open all the envelopes, and they look at who has the highest price. So first price sealed bid is the price which is the highest wins, and they pay that amount. Okay? That seems very logical, right? But there's actually a very interesting variation of this, which is actually even better. This is called second price sealed bid auction. So again, they all write the money on an envelope, on a piece of paper, they stick it in an envelope, they give it to the organizer, they open all the envelopes, the highest bidder wins again. Well, what does he pay? He pays the value of the second highest bid. That's very strange, right? He pays the value of the second highest bid. But actually, we'll see, this is very natural. We'll see that this is actually the best way to do auctions. So this was kind of a discovery, a very interesting discovery, and this was analyzed by an economist named Vickrey, and on this work he got a Nobel Prize in economics in 1996. So this is also sometimes called Vickrey auctions. It turns out these are actually more useful and they're more used than the first price. Seems very strange, huh? Why pay the value of the second highest? But we'll see. We'll understand how it works. Okay? So that's one thing. So there's 4 kinds of auctions. 4 types. Another thing, when do you do auctions? When you go to the supermarket to buy oranges, you're not going to make an auction. Now, all the people who want oranges will bid on a bag of oranges. No. No, that's not done. So when do you do auctions? Auctions are only done in a specific case. When the true values are unknown to the other people. So each buyer has some value for the item, and nobody else knows. It's my secret. Okay? And I don't want to tell my secret to everybody. So if the true values are unknown, nobody knows the values. They're all secret. The auction is a way of getting that value kind of out in the open. Okay? When you know the values, then you don't need an auction. The orange is €1.5 per kilo or whatever. No auction necessary because you know how much it takes to grow oranges and to ship them off. So when the values are known, you don't need auctions. Okay? And let me just explain a little bit how that works when the values are known. So let's say you have a seller and buyers, and they know the values. The seller says, I want to sell at least X. I want to sell at least €1. And the buyer says, I think it's worth 1.5. So the idea is that the seller has a minimum price they want to sell, X, no lower, minimum this or higher. The buyer has a maximum price they want to pay. They maybe want to pay less. So there's this area in between, and there's a difference between y minus x. So y minus x is called the surplus. It's the difference between what the seller wants for it and what the buyer is willing to pay. So that's like an extra amount. If the buyer can buy it at X, then the buyer has like a gain, wins y minus X, like a profit, surplus. But if the seller is able to sell at Y, then the seller gets y minus X. So So you see, this surplus is kind of divided between the buyer and the seller. This is like the extra profit. There's an extra profit there between what the seller wants to sell and the buyer wants to pay, and the maximum the buyer wants to pay. So this is called the surplus. Now, if the seller knows what the buyer's value is, if the seller sells at y minus epsilon, right here, well, the buyer is still going to buy it because it's less than their maximum price, but most of the surplus goes to the seller. So somehow, if the seller knows this, they get most of the surplus. But the opposite can also happen. If the buyer somehow says, I don't want to pay more than some amount that is less than y, then buyer will get some of the surplus. Okay? So this is the usual case when the values are known. So this is not auction. That you have this surplus and it's divided between buyer and seller, and y and x are like known values. So I explain it to you because this is the normal economics with no auctions. Okay? Now, sometimes you don't know these values. The y and the x is like unknown. So the seller doesn't know how much this famous sculpture costs, how much it's worth. Each of the buyers has their own private value for the sculpture. They don't want to tell it to the others because then it will raise the price, maybe. So everything is kind of secret. The values are unknown. So the auctions is like a way of getting some of that knowledge out of the open and actually buying and selling things. Okay, so the auctions are used when the values are unknown. Otherwise, you don't use auctions. Okay? They are a way of getting information on the values. Okay, so that's another thing. Okay, I'll give you now one more concept. Remember I told you there's 4 kinds of auctions. So there's the ascending, there's the descending, there's the first price sealed, and then there's a second price sealed. So these are different because both these are, this is interactive. This one is interactive. This one is not interactive, it's simultaneous. Everything happens in one instant. And when they open the envelopes, this one is also simultaneous. Okay, this seems kind of complicated, but actually, if you think about it, you can see that some of these are actually the same. So a descending bid auction is equivalent to first price auction. We can show that. And an ascending bid auction is equivalent to a second price auction. So, for example, this ascending and first price seal are actually equivalent. Okay? And descending, sorry, is that? No, sorry, I think I'm really wrong. Sorry for that. So the first price is equivalent to a descending. So I'll show it. Let's write it like this. And the second price is equivalent to an ascending. So let's see why. Okay. Take a look at descending auction, descending bid auction. The price is going down. Okay, it's going down, and nobody's saying anything. So nobody learns anything. Remember, an auction is a way of learning something about the price. The price that goes down, buyers learn nothing. Okay, while it's running. while the auction is running. The price is going down, everybody's silent. For each bidder, there is a first price that's in the end that they want to buy. Okay, that the first price that they have in their head. I want to buy the sculpture for 5 million, and there's another guy saying, I'm going to pay 4 million for that sculpture. So the price goes down, 6 million, 5.5, 5 million. The 5 million guy says, I bid 5 million, and everything's finished. Okay? So the very first price, the highest one, is the one that wins, and nobody learns anything else. Nobody learns anything. The item goes to the bidder with the highest bid, and the bidder pays that amount. This is exactly the same as a sealed bid first price. If all the bidders put their money on a piece of paper, and then the organizer opens all the envelopes, and he picks the highest one, it gives exactly the same result. Okay? So a descending bid auction is equivalent to first price auction. Okay? That's something you can see if you think about how it works. So these are two different ways of organizing, but theoretically it's the same thing that's happening. Okay? Now, let's look at the other one, an ascending bid auction, and a second price auction. So the ascending bid auction, the one that everybody knows, because you always see it in the movies, because it's very suspenseful. The bad guy raises the bid, and then James Bond raises a little bit more, so there's a lot of suspense. So they like to put this in movies. Okay? So consider an ascending bid auction. And I'm a bidder. How long should I stay in? Well, actually, as soon as the bid reaches my value, let's say I want to pay 5 million. As soon as the bid goes up to 5 million, if it goes higher than 5 million, I should drop out. Because I will lose money if I bid. Because for me, it's worth 5 million. I don't want to pay more. So you drop out when the price reaches your true value. Okay? And the guy who thinks it's worth 6 million will stay in until it's 6 million. Okay? But as soon as all of them drop out except for one, then that person wins. So the one with the highest bid is the one who stays in the longest. Okay? So the price goes up. 4.1 million, 4.2 million, etc. It goes up little bit by bit like that. When it reaches 5 million, I drop out. But maybe there's only one guy left, the 6 million guy, okay? The 6 million euro guy. As soon as I drop out, the 6 million euro guy is the only one left. So he wins. But he doesn't pay 6 million. He pays 5 million plus a little bit. Okay? The winner does not pay their true value. Does not pay what they want to bid. They pay the second. You see, that's actually how it works. The price is going up, 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 and maybe you have many bidders in the beginning, 10 bidders, and it keeps going higher, 1 million, 2 million. The bidders drop out. Then there's only 3 bidders left. 2 bidders left, okay? The 5 and 6 million bidders. And then it goes up to 5.1 million, while the 5 million bidder drops out. And the only one left is the 6 million. How much does he pay? 5.1 million. So he's basically paying the second highest price. You see that? So second price is very natural. See that? An ascending bid auction is actually the same as a second price auction. Okay? So the sealed bid second price auction is a simulation of an ascending bid auction. Okay? It's not exactly the same, but the result is the same. The highest bidder wins, but what they pay is the price of the second highest, the bid of the second highest. You see that? See how it works? It's very natural, huh? If you Have you ever done auction on eBay? Anybody has done auction on eBay? No? Nobody? So when you make a secret value, which is your highest value, and the bid goes up until some limit, okay? But when the time is reached, if the bid, let's say my highest secret value is 25 euros, I'm buying a book, and the bid goes up to 18.5, and I'm the only bidder left. Well, I don't pay 25, huh? I pay 18.5. So and that 18.5 is just a little bit higher than the second highest guy. You see that? So eBay is a typical ascending bid auction, and the winner will pay the price of the second highest bidder, plus a small amount, plus epsilon. So ascending bid is basically giving the same result as sealed bid second price auction. So basically, we only really have to look at these two, okay? We're going to look at these two. The first price and the second price. And these two are just like real-time versions, but with the same result. So we only have to look at those two, okay? So that's one thing. Okay? So these are the two auctions we're going to look at. So we're going to analyze them using game theory. Now, another thing is the true value. There's another distinction we can make. Each buyer has a private value in their head. Huh? I think the sculpture is worth 5 million, and this person thinks it's worth 6 million. Every buyer has the private value in their head. So this is called private value, because it's like the buyer's not going to tell anyone. The buyers have different taste, or they have different way of appreciating the item. Okay? But there's another kind of value, which is common value. Okay? So let's say the buyers are antique stores. And they buy the sculpture, but not because they want to keep it, but because they want to sell it. And so they don't really have a value. But they will try to see what is the value that I can get when I sell it. Okay? So that is like the same value for everybody. It's what it's worth when you sell it. So if the buyers are not keeping the item, but if they want to resell it, then they don't have private values. The real value of the item is the resale value, but it's still kind of unknown. It's unknown, nobody knows, but it's the same value for everybody. Okay? So there's two kinds of values. You see that? Buyers when they keep it for themselves, private value, and buyers when they want to resell. And then there's like one common value, which is the same for all the buyers. So this gives two different kinds of auctions too. Okay? So the strategies are different. So we'll look at private values first, and then we look at common values. Okay? So first, I want to look at auctions with private values. So this is the usual kind of auction, huh? Where everybody wants to keep the item, and nobody knows what the other person wants to pay, so everything is kind of secret. Huh? So let's take a look first at the second price auction in game theory. So now we're going to do game theory. So up to now, I kind of give you a course on what is auctions. Okay? So you know the different kinds of auctions and how it works. But now we'll use game theory to analyze it. And the first one I want to analyze is the second price auction. Okay? So the sealed bid second price auction. So this is really used a lot. Okay? eBay is doing that. Huh? When you win an auction on eBay, you pay the value where the second guy dropped out, actually. So you're paying the second price, huh? So it's a second price auction. And sponsored search markets. This is the big thing in the internet. So all the search engines. Google. Why is Google so rich? Well, because they do ads on their search engine, and that gives them a huge money flowing in, okay? They sell keyword-based advertising. They also use second price auction, okay? And we're going to prove a theorem. There's a theorem on this. Second price auction is actually a very nice one, easy to analyze. So the question is, what do you bid? Well, in second price auction, you can prove that bidding your true value is a dominant strategy. That means the best. You don't have to worry about anything else. If I think the sculpture is worth 5 million, my true value is 5 million, and I will go up to 5 million, and that's it. This is, you can prove it, it's a theorem. So the second price auction is really easy to analyze and prove, okay? The best bid is just what the object is worth to you. That's not the case for the other ones, huh? The other ones are much harder, but for the second price, it's very, very nice. Okay. And so we make a break, and then I'll show you why second price is so nice and why everybody uses it. Okay, left there at the equals. I want to first talk about the second price auction. This is the most widely used. First, before we get into the game theory, let me tell you how Google makes their money, okay? This is called sponsored search markets. And the guy who invented this had a really good idea, because why is Google having so many billions coming in? It's because of this, okay? Remember in the early days, well, you don't remember, but I remember in the early days, web search engines, they gave you useful pages. Fine. But some smart guy in the company said, hey, this is great for advertising. Let's try combining search with advertising. Because if people are interested in something, they search for that, well, it's the perfect way of making ads for that thing, because you immediately have the people who are interested, okay? So this is called keyword-based advertising, so pioneered by a company called Overture, but nowadays, this is Google's main source of revenue. So Google then tries to branch out and do all kinds of stuff, Android, whatever, Hotmail, whatever, but that's just fun and games. The real money for Google comes from advertising in the search. And the way it works is called pay per click. You see an ad, okay, you search, you see ads, but you don't pay. The advertiser only pays when a user actually clicks on it. So that's, the advertiser is really happy. If the user clicks, that means they're interested, okay? And it means the advertisers are willing to pay for that. You are going to find them an audience of interested people, okay? So there's many examples. So here, let's say there's this tourist place called Puka Lake, okay? And when they click on it, they go to your company's website. We were doing something related to that. And in 2010, clicking on that, each click, $1.50. It's a lot now. Each time somebody clicks, the advertiser pays $1.50. 1,000 clicks is $1,500. It's a lot, that. Calligraphy pens, $1.70 per click. You see a company selling calligraphy pens. If you click on that, it means you're interested. That's worth money for the advertiser. Okay? Even if you do typos, calligraphy pens, you go to the same thing, and you also pay because you will get some of the people. For some queries, it's huge cost. Mortgage refinancing. Okay, so I'm buying a house, and I buy the house, and every month I have to pay, and I lose my job, and I'm not earning much money, and I can't pay. I have to refinance my mortgage on the house. Okay, so I go to Google, I type mortgage refinancing, and I get companies that help me do this. If I click on one of those, that company will pay $50 for one click. It's a lot though. Or mesothelioma. Nobody cares about mesothelioma. What is this thing? But if you type that, probably it's your illness and you want to do something. And this is typically American. You want to sue your employer. This is the typical action. Something goes wrong, we have to sue somebody. Okay? So if you type mesothelioma in US, the top queries you get are law firms, lawyers. And they pay a lot if you click on their website. So that for them, it's a really good way of getting people. You see that? So this is how Google makes their money. All the rest for Google is playing around. Okay? This is the serious thing for them. This is where they make their money. And all the other stuff is just play, okay? So how does it work? Because you have to set prices. How do you set prices for these ads? How do you know how much it's worth? Nobody knows. Because it's unknown. So when everything is unknown, you do an auction. You see, the auction is a way of getting the secret information that's in the people's head, bring it out. So I have a piece of space on the website for mesothelioma. How much does it cost to put my link there? Well, all the companies who want to do that, they bid. And the highest bidder wins. But they pay the second price. Okay? So you have these slots on the web pages, and for each of the slots, you have multiple advertisers. But maybe the advertiser doesn't care if he's on the first slot. It's okay if it's on the second slot, because it's also less expensive. You're still on the web page, right? You don't have to be on the top. So it's more complicated. And maybe there's different advertisers for the different slots and for different parts of the words. If you do mortgage refinancing, maybe there's banks, maybe there's different kinds of companies that are interested in different parts of the search query. So it's not so simple. Okay? It's not a very simple option. So you have all these companies, and you have all these slots, and so they define a generalized second price auction, and it's called, and they don't do exactly second price, but they follow the second price principle. This is called the Vickrey-Clark-Groves VCG principle. Okay? So this is kind of generalized second price. So also, truthful bidding is dominant. That means bidding your true value. That makes it very simple, and the companies like that. They just have to bid what they think it's worth, and that's it. They don't have to do complicated analysis. So this is good. It makes bidding easy. It encourages truthful bidding, but it also makes it easy to bid, so the companies don't have to do complicated stuff. And so the VCG principle is like generalizing the second price. Each individual is charged a price equal to the harm he causes the other bidders. So this is similar to second price, So if bidder 1, so the winner, were not present, bidder 2 would win. And values the item at V2 would win. But bidder 1 is present, bidder 2 loses, doesn't win the auction. So the V2 is its value, is what the harm is. It's not really harm, but it's what bidder 2 kind of loses because of bidder 1. So the second price is like what is what the second guy is losing, okay? And the other bidders, 3 through N, are not relevant because they're always losing, so they're not harmed more. So this is giving exactly the second price rule. So this VCG principle is used for these complicated Google pay-per-click ads, okay? And with this, Google is making a lot of money, okay? Okay, so you see that it's important, and in fact, it's even ridiculous in some way, because when you look at a random web page, this is also used. It's not just used for search. When I look at a web page, you have ads, but which company is coming in that web ad? That is also determined by an auction. So when you look at a random web page, and the web page comes up with ads, for each of those ads, there's maybe hundreds of auctions happening. Auctions, all the time. So auctions is like always happening, huge amount. And why are all these auctions happening? Just for showing an ad, okay? Not something that's really saving the world, okay? Not that important. So a lot of the stuff that goes on internet and in the data centers is doing lots of work for almost nothing, just for ads, okay? And it's using this principle. So this principle is a big time waster for data centers and so on. But because people pay, it keeps going on. So a lot of money goes into this, okay? So this is, in my view, a very weird thing, but still we have to understand second price, which is the principle, okay? So what I want to do now is analyze second price as a game. Okay? So you have players. The bidders are the players. And each player has a strategy. And what is the strategy? It's the amount to bid. BI, okay, which is the amount to bid. And how do we determine it? Well, the bidders have true values. So the players are the bidders. Okay? The player is bidder. I will bid a value called BI. So that's the strategy. The strategy is to bid BI. So the bidder I has a true value of VI that's secret in their heads. But the bid is not secret. They have to tell Google or whatever. So they bid BI. So that is the move they play. So what is the right strategy? Okay. You can also define the payoff. So you have n bidders, each one bidding this. So that's like a strategy. You're all making a move. So you have an n-dimensional payoff matrix in this case, huh? So you can see this as an n-dimensional payoff matrix because you have n players. Okay? But I'm not going to draw n-dimensional matrix on the board, but I will define the payoff. Okay? Bidder I bids BI. If BI does not win, the payoff is 0. That's logical, huh? I don't gain anything. I don't lose anything. 0. But if BI is the winning bid, then I have a payoff. What is the payoff? It's my true value, which is VI, minus what I pay. It's what I gain, okay? So I think the sculpture is worth 5 million, but I'm paying 4 million, so I gain 1 million. So I get this 5 million sculpture, but I only pay 4 million for it. So it's VI minus BJ. BJ is the second place bid. Okay, it's the second price auction. So the payoff is 0 for the loser, and it's VI minus VJ for the winner. Okay? Right? You see that? You understand that, right? This is a game, right? You see how it works, huh? Of course, you can have ties, so there's a little bit of discussion here. How do you handle ties? If two bidders bid exactly the same amount, okay, well, we do some kind of tie break. Okay? We make an ordering on the bidders. So if B1 and B2 are both bidding the same, B1 equal B2, then, but if B1 is like the first in the order, so there's an order, then B1 will pay the same as, will pay B2, which is the same as B1. So the payoff is actually 0 in this case, so it doesn't really make much difference. The first and the second guys are the same, so the first guy wins, but the second guy has the same value, so the first guy doesn't really gain anything. Okay, so that's the detail. But this is the thing. The payoff is VI minus VJ. Okay, and now there's a theorem that we're going to prove. This is the second price auction theorem. This is one of the most important results in auction theory. So it's important to understand what's going on. In a sealed bid second price auction, it is a dominant strategy for each bidder to choose their bid BI equal VI, their true value. So each bidder bids their true value is dominant. What does that mean, dominant? It means that there's no other better strategy for that amount. Remember, dominant? So no matter what the other bidders do, I should always do that. It's dominant. So we're going to prove that. And the proof is not hard, but you have to have a clear head. So the proof. Okay? So bidder I bids BI, and BI is equal to VI, which is the true value. Okay? What do we have to prove? We have to prove that if we make a different bid, if we have another bid, BI prime, which is different from BI, that the payoff will always be less. Okay? Payoff for BI prime, always less. Actually, never greater is more precise. It will never be greater. It will be either less or equal. That's what we have to prove, huh? If we bid a different value, that we never get better. So we're going to handle this with two cases. One is where it's higher, is bigger than VI, and the other one where it's lower. And we're going to reason in those two cases. Okay? If we raise the bid, we will not get more. If we lower the bid, we will not get more. That's what we have to prove. Okay? So in both cases, the amount paid by the winner is determined by BJ. So the payoff, if I win, is VI minus BJ. So the payoff does not depend on this value. See, that's very important. The payoff doesn't actually depend on how much I made. It depends only on my true value and the second guy. Okay. So here's a diagram that explains the proof. But let me make this diagram, let me explain it on the board to make it easier to understand. It's not really very complicated. So let's have, we have a scale here. Okay, so these are the bid, the values of bid, of bidder I. So we have my truthful bid, which is here, where BI is equal to VI. This is the truthful bid. And then there's two possibilities. Either I can increase the bid, or I can decrease the bid. Let me make the colors correspond. I can do that. Either increase the bid, or I decrease the bid. And we're going to look at each of those cases separately. Okay? So it's called, let me call this one BI prime, and this one BI double prime. So either I increase the bid, or I decrease. So what do I have to show? I have to show that if I increase the bid, my payoff will not get higher. I have to show if I decrease the bid, it will not get higher either. Okay, so we have to now analyze this. And let's do the blue one first. Suppose I increase the bid, bigger than VI. I bid this, VI prime, which is greater than VI. What does it mean? Okay, how can it affect the payoff? So the trick is, how can this affect the payoff? Okay? How can it affect the payoff? It can only affect the payoff, okay? So if I lose with this, then I get zero, so it's nothing. So the only way that this can affect the payoff is if I lose here and I win here, right? The only way that it can affect the payoff is that if I lose here and I win here. Okay? Otherwise, it doesn't affect the payoff. If it doesn't change my win status, if I win here and I win here, it doesn't change anything. Because the payoff is VI minus VJ, remember? So if I win here, the payoff is not changing because there's no BI prime here, okay? So the only way that this can change the payoff is if it changes my win status. And that means that I lose here and I win there. Okay, you see that? Okay, that I lose with VI and win with BI prime. So if I win with BI prime, that means the second place bid has to be somewhere in the middle. Because if I lose here, that means the second place bid is more. But if I win here, the second place bid has less. So the VJ has to be here somewhere, okay, if I win. See that? So what's my payoff? What's my payoff if I win? It's VI minus VJ. Ugh, that's negative, or less than or equal to 0. That's not good. Huh? So if I win here, that means the second place guy is here, and that means I lose money, because the second place will be higher than VI. So if I increase my bid, all I can do is lose. See that? You see the reasoning goes in 2 steps, huh? First of all, the only way the payoff changes if I change win status. Okay, which means I lose here and I win here. Because if I win in both, the payoff will not change. There's no BI in here, in this payoff number, okay? So if the win status changes, and if I win here, then the second place has to be somewhere in the middle, and then VI minus VJ is negative, so that's not good. I'm not gaining anything. So increase will not increase my payoff. Okay, you see that? That's the blue case. And you can handle also the green case. The green case is when we, let's say, we decrease and the bid, and can this increase our payoff? Good question. Okay. Well, if I decrease the bid, if the payoff status, again, does not change, the win status does not change, then the payoff is the same. It's VI minus BJ. There's no BI in here. So the win status has to change. Okay? And how can it change? The only way, how can win status change when I reduce the bid? The only way it can change is if I win here and lose there. Because when I decrease bid, it cannot make me win, okay? It can only make me lose. Okay? So the only way is that if this one was a winner and this one a loser. Okay? If that's the case, the second place guy has to be somewhere here. Huh? Somewhere here. If this is a winner and this is a loser, the second place guy has to be there. Okay? So the payoff before descending was VI minus BJ. And the payoff after was 0. Because I'm losing after, right? So clearly it's not increased, okay? This one can be greater than 0, but after it's 0. So that means in both cases, the payoff will not improve, okay? So it's important to understand this. Question?
Si chaque joueur respecte la stratégie dominante et joue sa vraie valeur, qu'est-ce qui se passe si les deux plus hautes, c'est des gens qui misent la même chose?
Ah, c'est ce qu'on a dit. If the two highest ones bid exactly the same value, then we need some kind of tie-break strategy. Right, so this is what I explained here, okay? The ties. So you have to make a tie-break. So you have to give some kind of order to figure it out. So if the first and the second are the same, then one of those two guys will win, but he pays the second guy. But because the second guy is the same, he's actually winning 0, okay? So the tie is actually not a good situation. The winner is not actually gaining anything. So if both people bid 5 million for the sculpture, then one of them wins and pays 5 million. But their payoff is 5 million minus 5 million, 0. Okay? So tie is actually not good for the winner. Right? They don't really get any. They win, but they don't actually get a positive payoff. They get 0. They still get 0 payoff, but they get the object. So there's still kind of a gain, no? But they don't actually. They've transformed 5 million euros into 5 million sculpture. But it's the same value on both sides, okay? So they don't actually give any extra value. That's the case of a tie. But if there's not a tie, then one of them is actually, then the top one is actually getting something, yeah? Getting a gain. Okay. Okay, so this is, this proof is something that really shows why the second price is a good idea. The payoff is VI minus BJ. So the trick, if you want to see it, is there's no BI in here. If BI changes, it does not change the value of the payoff. The only thing that will change is if I change from winner into loser, then I have a different payoff. But if I just change a little bit BI, it will not change the payoff. Okay? Okay, so that's the second price theorem. So this is the most important. This is the most widely used one. So this is the most important one. Okay? Let me now talk about the others. The others are harder to analyze, so I'm not going to analyze in detail. I'll just kind of say some things. First price is also used sometimes. Okay? I mean, not for advertising, but it's sometimes used, but it's very different from second price. Okay? And why is it so different? Well, in the second price, the value of your bid determines whether you win, but it does not determine how much your payoff is, okay? Sorry, but not how much you pay. I'm not saying that right. The value of your bid determines whether you win, but it does not determine your payoff. Okay, I'll fix that. In the first price auction, the value of your bid determines whether you win and also your payoff. Okay? So here's the first price. Here's the game theory. So the bidders are the players, just like before. The bidder's strategy is the amount they bid, just like before. But the payoff is different. Okay? So if you lose, you still get payoff 0, same as before. But if you win, if I win, I have to pay what I bid, so the highest. So the payoff is VI minus BI. I have to pay what I bid, not what the second guy did. See, instead of VI, BI, the other one is VI minus BJ. Okay, that's the big difference. Okay, so the payoff will be less, of course, because BI is going to be higher. But it's harder to analyze. So how do you bid in first price? It's not the same as second price. Bidding your true value is not dominant anymore. Why not? Well, if you lose, you get 0 payoff. But if you win, if you bid your true value, then BI is equal to VI, and your payoff also is 0. So that's not good, winning 0, okay? So bidding your true value is not good. So what is the trick in first price? The optimal way is to make your bid a little bit less than VI, and then VI minus BI will be positive. So you get some positive payoff. But you can't make it too much less, or you lose, because you're lowering the bid. So there's two forces. If you bid too high, too close to your true value, you win less. And in the limit, you win 0. But if you bid too low, you reduce your chance of winning. So you have to bid a little bit less than your true value, but not too much less. So it's kind of tricky. So I'm not going to make formal analysis, but you have to understand the intuition. If there's a lot of bidders, lots and lots of bidders, then by chance, the bids will probably, there'll be some very high bids, okay? Because there's, by chance, if you have a lot of them, then some of them are going to be higher, so your bid should be higher. But if there's only a few, small number of bidders, you can make a bid lower, okay? So this one is not easy, and that's why it's not used. So on the internet, this one is really not used, okay? And then the final one for private values is another neat one called all pay auction. This one I know because I did it myself. This is a funny one. In the all pay auction, you always pay your bid. That means if I bid BI and I lose, I pay BI. That means the losers will pay. Okay? That seems weird, right? If I win, then it's like first price. What I gain is VI minus BI. But if I lose, I actually pay BI. So all the losers have to pay. That seems weird, but actually it happens a lot, this kind of game. For example, I'll give 3 examples. Political lobbying. So the lobbyist wants a certain law to be passed and spends money for that, contributes to political parties and so on. But only one of the parties will win. But the lobbyist, the money they spent is gone. The lobbyist will always spend the money even if they lose. or a design competition. We're making competition for a new building, and all the architects are making designs, and one of them wins. But all of them, they spend money making the designs, working on it. So that money, they don't get it back. All of them will always pay, but only one of them wins. Okay. See, so this all pay option seems kind of weird, but it's actually a common thing. And the third one is, this is what I did sometimes, research projects. So the European Union gives lots of money to professors like me to make research, do research. So I had a project called Light Cone, and I got 3.5 million euros for that. Not bad, huh? I mean, it's not money I put in my pocket, but you can hire people and so on. But I wrote a proposal for that with the help of the partners. I spent a month, more than a month, working on that proposal. That's a lot of time and effort. Okay? But if my project is not funded, they're not going to reimburse that. See, so I always lose that money. Okay? So this is, all pay is kind of an interesting variation on first price. Okay? So it's kind of a first price because you will, the true value, 3.5 million, but I spent already a month working on it. So I will gain 3.5 million minus a little bit. But or I lose, and I get just minus VI. Okay? So all pay is like first price. Okay? Similar to first price, except that you bid even less, because if you lose, you pay. Okay? So that's an interesting kind of bid, all pay, an interesting kind of option. This one is used a lot. You can see where it's used. Okay, so let me make now a summary of the first part, which is the private values. So each bidder has their private secret value, and then they bid. So the secret value in their head is VI, and they bid VI. We saw three options, second price, first price, and all pay. So second price, the payoff is VI minus BJ. First price, the payoff is VI minus BI. And if you all pay, it's also VI minus BI, but you lose BI if you're not a winner. Okay? In the second price, the dominant strategy is you bid your true value. Here. And in the first price, the best, there's no real optimal strategy, but the best bid is usually slightly less than VI. And in all pay, it's also less, even a little bit smaller, less than VI. Okay? These are hard to analyze, so they're not used on internet. Okay? All pay is used in real life, but it's not really used on internet so much. The one on internet is second price. That's used a lot in internet. Okay? So that's the first part. That's when the bidders have private values. Let me now finish with something which is kind of neat, which is called the winner's curse. This is common values. So now we go away from private values, and we assume that the object, that it's the same value for everybody. I mean, for example, there are antique stores, and they will buy the sculpture, but they don't keep it, they sell it on the open market. So they're all selling it, all these stores, so that thing has some value on the market. So for all the stores, they have just like one common value. They don't have a secret private value, okay? So this is common value. For example, the bidders try to resell the object. They have a common value, but they don't really know exactly the value, okay? The bidders, this common value, it's not like it's written on the sculpture. It exists, but they don't really know it. So the stores, the antique stores, they have some idea of what it is, estimation. So each bidder has some idea, VI. So V is the true common value. But VI is the estimate from the bidder I. So maybe they're not exactly right, And xi is some error. It's a random number whose mean is 0. So there's some kind of fluctuation around v. Some stores have high estimates, some stores have low estimates. Okay? So the common value, all the bidders have some idea. Okay? But this is actually very weird. Okay, here it is. What happens? Assume that this sculpture is sold with common value in a second bid, sealed bid second price auction. Okay? So the bidder is not going to bid VI anymore. It's not a dominant strategy anymore to bid VI. Why is that? Well, you have all these bidders, and they all kind of know what the common value is, but they have errors. So some of them will overestimate the value, and some will underestimate. And probably the winner will be one who overestimated it. This sculpture, I think it's worth $5.5 million, and the other store says, no, it's only worth $4.5 million. So the guy who overestimates is going to win. Okay? But the real common value is less than that. That means the winner will pay $5.5 million, and then when he tries to sell the sculpture, he will only get $5 million, because that's the common value. So he loses $500,000. So the winner is losing. You see what's happening here? Because they're all estimating, like a cloud of estimates, the higher estimate is going to win, but probably that's not good. It's an overestimate. So when they actually try to sell the thing, they get less. This is called the winner's curse. Okay, this is a famous notion. It's called the winner's curse, and it's a typical thing for common value auctions. When bidders want to resell the item, you have to be very careful because you have a winner's curse. Okay, and there's other examples. Let me give you some more examples of it. So petroleum industry or sports. So let me tell you first the sports one. Baseball, it could be soccer. Baseball are buying baseball players, champion baseball player. And the common value is how good is that player, his future performance. Okay, so you have 5 clubs, they want to buy this baseball player, and the one who overestimates is going to get the player, but the player is going to underperform compared to that. Winner's curse. So there's another example. So this is an example that happens a lot. Oil field. Okay, assume you have this field and there's oil underground, but nobody knows exactly how much. You can estimate. So the geologists, they estimate. Okay, assume that there really is $10 million worth of oil underground. But the oil companies, they don't know that. They guess. Some oil companies say, there's 5 million. Another one says, 20 million underground. So the guy who estimated 20 million, he's going to win the auction. Wow, isn't he happy? But there's only 10 million worth of oil in there. So he's going to lose money. In some cases he might not. If the second price is less than 10 million, but if there's a lot of companies, probably that's not going to happen. He's going to pay the second price. But usually the second price is going to be also more than 10 million. So the guy loses. Okay? Winner's curse. Happens a lot. Spectrum auctions. So again, like I mentioned, the government auctioned radio spectrum for Wi-Fi, for whatever, or GSM, mobile phone. The company buys the spectrum and says, I'm going to make billions out of the mobile phones on this spectrum. But maybe they only make 0.8 billion, okay? So they lose, okay? Also, selling shares of a company. Maybe you haven't done that, but when a company goes public, they sell shares, and you can buy the shares. How much are those shares worth? Depends on how good the company is going to do. So the one who overestimates is going to get the shares, but maybe the company is not going to do that well. And there's more examples, like orange juice, supermarket chain, Deleuze. Deleuze buys 10 million liters of orange juice. Okay? And I am an orange juice producer. I want Deleuze to sell my orange juice, and so I have a low price for my orange juice, but I only have 3% profit margin, but it's okay. But then there's a hurricane, and all the orange trees are down, and the price of oranges goes way higher, but I have signed a contract for my orange juice. That means I'm losing money now, okay? So the winner is losing, okay? Okay, so what do? Of course, smart companies, they know about the winner's curse, and they try to somehow calculate it into their bid. So a smart company, which I call a rational bidder, should lower their bid a bit so that they know winning has to be better than losing, of course. So usually the bids will go down a little bit, just in case, okay? But it's very complicated. If you want to analyze that kind of stuff, so we're not going to analyze. But smart companies will take it into account, but it still happens, winner's curse. Okay, so now let's summarize. So we saw a lot of stuff today on auctions. So I started with transportation network, and I showed Braess's paradox. But then most of the course was about auctions. So two kinds, private values, common values. And in the private values, we saw three kinds of auctions: second price, first price, and all pay. And the second price is by far the easiest one and the best one to use. So most internet is using this one. And the reason why it's very easy for a company to use this is they just have to bid their true value. That's very easy. Otherwise, it gets much harder, okay, for first price and all pay. And finally, common values is nasty because you get winner's curse. Okay, so there we go. So let me stop here. So now you know a lot about auctions and about internet, and a lot of internet computation power is wasted on these auctions. Maybe not wasted. I mean, Google is making lots of money, so they would not agree with me. Okay, but a lot of computation power is being used on this second price auction. Okay. Okay, so let me stop here. Thank you.